Justin Miller, Oxnard College Physics here, and we're going to go ahead and look at some more items regarding resistors, resistance, and resistive circuits. So, first off, what do resistors do besides just control the current? Well, they can do various things besides controlling the current. Think about an incandescent light bulb. Hey, what happens? You make some current go through it and it lights up. Ooh, why does it light up? Because there's a nice little tungsten filament, usually, that the electrons go through and they start heating it up. It gets really hot, really super hot. Anybody ever touched an incandescent light bulb before after it's been on a while? You probably only do that once because it'll burn the heck out of you. But anyways, that little filament gets really hot, so hot it starts glowing white. And there you go. We've got some light made with electricity. Well, electricity does all sorts of other things too. We have it spin motors and open doors for us. Use it in toaster, heating elements in toasters, stuff like that. But generally speaking, what do resistors do? They dissipate energy over time. They transform energy into other states. And yeah, that's kind of a consequence of the resistance forcing electrons through some little cross-sectional areas tends to make things hot. So generally, resistors will heat up over time. Depends what environment they're immersed within. We generally have that, yeah, resistor's going to heat up. That's not all that they're used for, obviously, but it's one effect that generally does happen. So as current goes through a resistor, dissipates energy. Transforming kinetic energy of the moving charges into other forms such as, well, heat. It's not the only form, but that's the big general form there. Also, this current goes through a resistor. Resistor will generally get hotter. Again, this sort of depends on what sort of environment it's immersed within, what its temperature already is, things like that. But the general aspect is that, yeah, you force electrons through some material, and there's kind of like this internal friction in a sense, and that tends to heat things up. So, tend to get hotter. Well, most materials will have changes in the resistivity due to changes in temperature. The general consequence is, as a material heats up, its resistivity increases, thus the resistance of that segment of which that material is comprised increases as well. generally as temperature increases. Rho increases. Thus the resistance increases. So we've got a few things going on here. We've got energy being transformed into other forms over time, and that's dependent on the current, and it's dependent on the resistance too. We can always go back and think about, well, potential difference, how that's correlated with potential energy, changes in potential energy, and then sort of put a couple little things together in terms of charge times potential difference, change in potential energy. We divide changes in energy divided by the time over which the change occurs, and we got ourselves a whole new ball game. So, consider this. Consider a potential difference across a resistor which thus produces a current. Through the resistor. So we can take ourselves a resistor here, we can say, hey, there's some potential difference across this resistor. We can go ahead and call that delta V sub I. We'll say that that's the plus side, that's the minus side, that doesn't really matter. We have that this resistor has some resistance R, and we've got the current that's going through the resistor right there. All right. Delta PE is equal to a Q delta V. Remember this? Changes in potential energy are equal to the charges that move through some potential difference. Well, what charges are moving through this potential difference in this case? Well, all the charges that constitute the current. This is a bunch of charges moving with respect to time, coulombs per second. So how can we sort of change this into something else? The change in potential energy per unit, we'll just say delta T is going to be equal to Q delta V over delta T. And this would then be energy per unit time. Well, how can we make some sort of consequence out of this? Let us define the quantity called power. Energy per unit time is defined as power, P. We use this kind of scripted P for it. So this we can go ahead and say is power. Energy per unit time, energy delivered per unit time to the resistor, or in the same sort of way, the energy dissipated by the resistor per unit time. This is the power supplied or power dissipated by a resistor. What's that going to be equal to? Well, we've got this thing. Power is going to be equal to this Q delta V over delta T. Well, delta Q over delta T, let's do dt, delta T, what's that equal to? Current, I. So what do we end up with here? We can say that the power is equal to I times delta V. Delta V is the potential difference across the resistor that is dissipating the power due to the current going through that resistor, as this, right there. So we could change this to a little sub R, just so we know that we're talking about that particular resistor. So the current multiplied by the potential difference across the resistor is how we can compute what the power delivered to that resistor is, or the power dissipated by that resistor. There's another way to write this out. We can also write this as P is equal to I squared times R. And a lot of times you'll see it in this form. Just call it I squared R loss. The energy per unit time lost to the resistance in the circuit. And that's pretty much that. But this is another form. How do we get this out of this? Via Ohm's law. All right, so there we go. We got a correlation with power, energy per unit time. What are the units of power? That's something that's important. SI units of power. Well, and we got our script P there, and that has to be equivalent to current, which is amps, times potential difference, which is volts. Amps volts. Well, that doesn't seem super duper helpful, but what could we come and look at as well? Well, that's correlated with energy per unit time. This side and that side have to have the same overall connection. So we can also write this as units of energy per time, which is joules per second, which is equal to 1 joule per second is equal to 1 watt. Use capital W for. So the SI units of power are the watts. How many watts? You say this is a 50 watt light bulb. That means that it used 50 joules of energy per second. That's what that means. So this is how we generally talk about energy per unit time in electrical systems. Watts. All right, so there's one last thing with this, and that is to note something that we said before, in that, hey, as a resistor heats up, or as a material heats up, conductive material heats up, we tend to find that the resistivity increases, and thus the resistance of that segment also increases. So there is what is known as the temperature dependence of resistivity, or temperature dependence of resistance. They're basically the same formalization. And we have this change in resistance, due to temperature changes. It's given by R is equal to R sub 0 multiplied by the quantity of 1 plus alpha times T minus T0. So then you say, well, what is all this stuff? We've got ourselves. R is the new resistance at the new temperature T. R0 is the reference resistance at the reference temperature. T0, and then we've got ourselves alpha here. Alpha is called the coefficient temperature temperature coefficient of resistivity. And why not resistance? Well, again, because resistance is directly correlated with resistivity, we can replace this and this with resistivity because we have the same L over A, assuming that the length, the spatial dimensions of the resistor don't change, which actually they do a little bit, but this is just a first order approximation. One can also write that rho is equal to, that's not rho, that's going to be confusing because that looks like P for power. Rho is equal to rho 0 times 1 plus alpha times T minus T0. So the temperature dependence of resistance, temperature dependence of resistivity. In either case, the coefficient is the temperature coefficient of resistivity. And that is, depends on the material that's being used. So the one kind of a neat effect that comes out of this is as the resistor heats up, the resistance increases. What happens then when the resistance increases? Well, as this gets larger, this gets smaller, and this is squared. So what turns out being the case here is as the resistor heats up, the resistance increases, the current then decreases, which means that the power, the energy dissipated by the resistor decreases as well. So it uses less energy per unit time, or dissipates less energy per unit time when it's at a higher temperature. That doesn't mean it's more efficient, it just means that it uses less energy. That may or may not be preferable. Generally, when things are hot, in terms of a mechanism, electronical mechanism, they run less efficiently when they're hot because you get all this background currents, there's all sorts of stuff that go on. But anyways, it is kind of a cool effect that has some applications. I usually bring up light bulbs, incandescent light bulbs. Anybody ever seen an incandescent light bulb burn out? I have, many times actually. Well, out of the people that have seen that, did you see it when you first flipped the light switch on, or did it burn out after it had been on for a while? And if we took a poll of a pretty good sample of people, we'd find that the majority of people actually would say, oh, I've seen it burn out when I first flip on the switch more often than when it's just been on and it burns out. Why is that? Well, when you first flip on the switch, the incandescent bulb uses much more energy per unit time, there's much more power delivered to it than when it's hot, working at its operational temperature. So when you first turn it on, it's cold. It's room temperature, right? And for a very brief moment in time, it's got to go from that room temperature to that very high temperature that it operates at. But right when it's very low, it has a very small resistance, that's a very large current, thus the power being supplied to it is very large. So the tendency is more for it to burn out then than after it's just been on. Now, obviously, it can burn out when it's been on for a long time too. It has to do with the degradation of the filament that occurs over time due to heat and the electrons going through it and stuff. But you'll find that it is observed more often that the filament burns out when you flip the switch on, other than, or compared to when it's just been on for a while. Some of it depends on how long it's been on. Other factors. Anyways, that's kind of neat to think about. And leave it at that for now. And there's more to come. Take care.